Okay, so good afternoon, everyone. So welcome you to study robotic course. So today is a public holiday. This is why we undertake today's lecture online. And today's lecture will be recorded, right? For those of you who could not join today's session, will be able to watch the recorded video, okay? Today I'm going to give you a quick introduction about this course. Then the key takeaway from today's lecture is about the study of Module 1. So for Module 1, we will try to clear Lecture 1, Lecture 2, okay? Because we have a very tight schedule, okay? So let's start with a quick introduction or overview about the robotics course, okay? So inside Until Learn, you should be able to access to the teaching material as well as a teaching plan, okay? So this course will be taught by two instructors. So I will help you to learn in the first 6 weeks. Then subsequently, Ahmad will continue to help you to learn robot kinematics, robot dynamics. Okay, so in the first 6 weeks, actually you will gain a big view, overview, big picture about the 3 modules, which include robots, advanced body, advanced planning, and advanced control. Okay. Then for the remaining study after 6 weeks, basically you will continue to study module 1, but the theoretical part of module 1. Okay. So when you talk about the robot kinematics, robot dynamics, basically you need to have a basic knowledge about the mechanism, right? Once you know mechanisms, hardware aspect of a robot body, then you are ready to continue to do the study about the kinematics dynamics. Okay. In terms of assessment, the CA will occupy 60% and the final exam will just occupy 40%. Okay. So let this slide help you to understand the distribution of the weightage for the assessment. Okay. Then as an NTU student, you need to know what is NTU's mission, right? So the mission include education, research, innovation, right, and enterprise. So this course actually will give you competitive advantage to venture into startup, right? Because today robot is very, very hot topics, etc. Right? And the NTU also want to become the house of talent, hub of a global impact. Then how to achieve a global impact? One way is to kick off impactful startup, right? So that should be part of your mission, right? As an NTU student, try to see whether you should be able to venture into the business world, right, with a startup. Okay, so then in terms of the mission, so you will see education, research, right, and the the accumulation or training of the talent and the production of impactful outcome in terms of research and techno entrepreneurship, etc. Right? Okay. For you, okay, it's very important that you must know what is your mission as MAE student. Okay, so this is the basic version. Try to remember the keyword of design, machine, controllable behavior, and intelligent way, right? Okay, so as MAE student, in future and during the interview by your future employer, right? You should be able to tell your future company that you are able to design machine, right, with controllable behavior. Okay. Based on this mission statement, at least you understand this course actually help you to assess yourself to what extent you have achieved your mission. Okay, because this course help you to know, okay, to what extent you are able to design robot, okay, with controllable behavior, right? Okay, so it's very, very important. And then how to fulfill your mission. This slide is extremely important. It gives you the guideline for you to achieve your mission. And most importantly, this slide help you to prioritize the study of courses. So from this slide, immediately you understand the number one course for you to take should be control theory, right? The number two should be sensor. Number three should be microcontroller, right? Then number four is AI. It's a perception planning. Perception planning belong to AI. Okay. Then number five should be robotics, all right? Then because robotics basically is a course which help you to see whether you are able to consolidate what you have learned so far, okay, into the design of machines such as a robot, okay? So at least this slide help you to understand what are the courses you have to take, right, as an MA student. In case if you have not yet taken some relevant courses, then you have a quickly catch up. And for system under control, this could be a mechanic system, right? So this is why you need to learn mechanism, design of mechanic system, etc. Okay, so it's quite important. Then my role here is to help you to do the study, right? Don't treat me as an assessor, right? I'm not here to give you the pressure. I'm a helper to you. Okay, so you feel free to approach me in case if you have a difficulty to understand certain concept. Okay, then for my background, if you look at this slide, you see I published a book in robotics in year 2003, a book in AI in year 2021, and I have jointly set up a Robotics Society of Singapore, and all of you are encouraged to become the member of Robotics Society of Singapore if you are interested in robotics. Okay, so this gives you a little bit of background about myself. But in terms of a basic research, my focus is on authentic AI. Then from this slide, you have to pay attention to the speculation of fake AI. I believe 99% of people in AI community are doing fake AI. They do not know what is authentic AI. Okay, so this slide help you to pay attention now. What is authentic AI? What is a fake AI? Okay, after the study of robotics, at least you will be able to understand the pillar number 4 of authentic AI. You see, there's a yellow drawing there. There are 4 vertical pillars. Pillar number 4 actually contribution come from robotics. Okay, is a motion planning. That is a typical example of pillar number 4. If people do not know what is a pillar number 4, how could they claim they know AI? Okay, so you see, robotics help AI community to venture into right direction. Okay, clear. Then the application of AI onto physical system, right? There are many opportunities. One is to apply AI to or inside humanoid robot. And here you see the prototype that we have developed from small humanoid robot to the full-size humanoid robot. Another interesting platform is autonomous vehicle, which include autonomous surface vehicle, right? So NTU has a team now, Robotics team now, right, which participate to the international competition. And this year, the competition will be held in Singapore in November, right? Okay, so you have a land vehicle and a surface vehicle, etc. So this is a good platform for us to apply AI, etc. Okay, but in terms of important breakthrough, right? We have achieved, this is very important breakthrough in robotics, and under the title of XI coordination. X could be hand, head, body, whatever, right? So we discover this solution in year 1997 10 years later, this has been validated with the monkey, right? And a few years ago, we have fully proved this solution. This is a very, very important discovery like in AI or in robotics, okay? And the second breakthrough is about the understanding of a photo, interpretation of a photo image, right? For human being, when you see a picture and the output in your mind should be three-dimensional scene, right? Then what is the working principle behind it? Or what is the mathematics behind such a mental process, okay? So we have discovered the mathematical process behind it, okay? So you can find the detail of this breakthrough in my robotics book, okay? And the third very important breakthrough is about the large knowledge model. Today, a lot of people talk about the large language model. That is a misleading terminology. Language is a tool for us to use. Why are we going to model it? It's a tool for us to use, okay? What we need is a large knowledge model, okay? So this slide showing you the blueprint for the design of a large knowledge model, okay? Which include knowledge in the physical world, knowledge in the conceptual world, etc. Okay, so here are some demonstration of humanoid prototype that we have developed, etc. Okay, so and through my website, go to YouTube, you should be able to watch all this video, okay? In order to save time, I just skip this one. And this also is a collaboration project with Fuji University and the Fudan University, right? So this is the development of autonomous lab vehicle. And the Chinese TV, national TV has been report on this project.
他们的作品涉及自然科学、哲学、社会科学、科技发明制作等领域类别，代表了当代。
Going up, and okay, the school has used some of our research outcome now to do publicity in order to attract researchers to join MAE, etc. Okay, so that's about the NTU, about you, about the me, all right? Then now I'm going to give you a quick overview or introduction about this course, okay? So there are two instructors who will teach you this course, okay? I will cover the first 6 weeks. Then Amma will teach you the remaining 7 teaching weeks, okay? We talk about the teaching week, but there's one recess week, okay? Something like that. Then for robotics course, this is very, very important because the robot is a typical machine, okay? And then there is a debate about how to achieve the greatest creature in the nature. There are two suggestions. One is bottom-up evolution. Another is a top-down design. Okay, I do not know how many of you still believe in the bottom-up evolution. Okay, so the more you do in robotics, the more you will believe in top-down design. Okay, so design is the key for you to achieve any kinds of a creature. It is not bottom-up evolution. Okay, forget about the bottom-up evolution. Okay, so this is advice to you if you still stick to this old concept of a bottom-up evolution. So actually, this tree of life is wrong, okay? It's not correct, okay? So it's misleading. So this is just something for you to know. Then you may want to know, okay, what should be the greatest creature, okay, which could be made by a human being? More or less should be robot, right? A machine which has a similar capability like a human being in terms of behavior or physical behavior and the mental capability, right? Okay, so that will be the answer. Now look at the history of robotics, and this is one version which telling you the history of robotics, and this version put the history of a robot which will be or which was started in 1495 or something like that. Okay, you just watch this short video. You see 1495 to 2100. Mechanic duck. The first patent in robotics, the first industrial robotic arm. First mobile robot. Maybe the first humanoid robot. Next robot. Okay, so let me here give you one version of description about the robot history and also about the projection of robot history in future. Okay, so actually we could rectify that version of robot history. Okay, if we consider teleoperated robot is a part of the family in robotics, then we must consider the buffer, all right, is first generation of teleoperated robot. Then in this case, we can, okay, push back the history of robotics back to uh, a year around 1000 or 900 or 800, something like that. Okay, so that means the history of robotics is much, much longer than what has been shown inside the video. Okay, it's just for you to know. Then what is a puppet? I just play a little bit of video for those of you who do not know what is a puppet, all right?
A long time ago, a monarch missed his deceased concubine so much, he got sick. His ministers reproduced the image of the concubine with cloth and put it behind a screen. The monarch could see the shadow of his concubine on the screen. This was the origin of the shadow puppet. 皮影 represents interesting stories with lively songs and shadows produced by lights. It is the earliest animated technique in the world.
Okay, should be good enough. So in the video, you say animated technique. That is not correct description. It's teleoperated, all right? Again, teleoperated demonstration. So it should be considered the first generation of a teleoperated robot. Then here you see the teleoperated arm in 1948. This should be considered as a second generation of a teleoperated robot. Okay, and this slide summarizes a little bit what you have seen inside the video, right? So the birth of the terminology of a robot was in 1921, and in year 1941, 42, then there was a birth of terminology of robotics, and also Asimov is a writer, has formulated the three roles for robot to obey, right, to follow, etc. And in the video, you also know that there was a first patent in robotics, first company in robotics, etc. And all the way to today's situation, we have this Boston Dynamics humanoid robot at last, etc. Okay, and then this is just a short history of Boston Dynamics robot. I just play a little bit. Yeah. Okay, should be good enough. And in Asia, Japan is a particular country with a special interest in the development of a robot. And the Japanese government invests a lot, right, to push the development of a robot and all the way toward the commercialization, right? Then you see they started their interest, right, from the play of a Piyin or shuttle puppet. Shuttle puppet actually was developed in China, right? They continue this tradition all the way toward the development of today's generation of a robot, etc. Okay, for a single company, you see this is the history of the development of a robot by Honda, and here you see some very advanced demonstration, right, made by Honda's Azimo humanoid robot. Okay, so all this video you can find from the YouTube. I just quickly go through. Then in Singapore government also invests a lot, right, into the development of a robot, and NTU, NUS, and the other university in Singapore, they also have a lot of interest in the development of the robot system. Just now you have seen this demonstration, all right? I just skipped. Then you may ask yourself, what is definition of today's robot? So here I just showing you three key points inside the answer. Robot must be able to execute motion. So therefore, immediately you understand, robot must have this mental capability to transform description of a task all the way into description of the motion. Okay, immediately you understand. Then through the execution of the motion, robot gives the impression that they are able to perform a task. So immediately you understand task motion are strongly related to each other. Okay, for today's robot, one more capability to aid in, okay, on top of an industrial robot, it is this interaction with people. But interaction could occur at the signal level and also at the knowledge level. And today, what we talk about the interaction should be interaction at the cognitive level. That means use of human language. So from this slide, immediately understand, okay, language is a tool for us to use, right? So language is not the target of research or study for us, okay? And why robotics is so important, this is a projection of business, right? Potential with the deployment of a robot. Then there's another answer. If you look at the evolution of human society, okay, today we are in the internet integrated society, then we are entering AI integrated society, then the future should be robot integrated society. In the video about the history of a robot, the last sentence you see, robot civilization, okay? So in my terminology, it should be robot integrated society. Okay, clear. So with robot, there's a lot of application. I just skip all this, right? So you can do a lot of things. Material handling, welding, soldering, right? And operation of a CNC machine, right? And in all the car, automobile, this is a typical industry which will deploy a massive amount of robot, right? Eventually, they could achieve a manned factory. How to achieve a manned factory? Basically, is to deploy a robot, right? To undertake a job which could be done by human being. Okay, I just play a little bit this video. Then you see in the production line, you see the massive deployment of a robot. Almost no presence of a human being, right? So this is a typical scenario of a manned factory or a manned production line. Okay. You will see a zoom out view that gives you an impression about the number of a robot in this factory floor. I think. So the robot is doing welding, right? Okay, this is a factory floor, right? So almost no presence of human worker, right? So you have an idea, right, about the amount of robot inside Okay, the factory. Okay, good enough. And in medical field, in the home environment, service robot, and in future, the automobile industry will become part of the robotic industry, and in future, a vehicle will become a high-speed mobile robot, right? So this is a demonstration done by us in NTU 20 years ago, around the year 2000, right? So this at the B4, right? Just next to the MAE Innovation Lab, right? You can recognize this role, right? So this is a video almost 25 years ago, right? What we have done now, right? This is demonstration, okay? And this is just for you to think, right? Is our intention to use robot to replace a human being? The answer is no, it's not to replace, it's to free us from doing those dangerous, dirty, difficult job, right? Must use free to free human being from doing the work which are not so pleasant for human being to do. Okay, then we can undertake design, marketing, and the sales, right? And free human being from the production line. That should be the intention. Okay, you should tell people in this way, right? It's not to blindly replace a human being, because the robot can extend our physical capability, extend our mental capability. Okay, that is the intention. Okay, what will be the outcome of this course? And basically, is for you to be ready to follow industry evolution. All right, today we talk about the industry 4.0. Then what should be the industry 5.0 or 6.0? Okay, I believe robot integrated manufacturing will emerge sooner or later, right? So, and then this video give you a rough idea about what do we mean by manufacturing. I just play a little bit of video, okay? At least you know what is a production line. Good enough already, right? So in this production line, there are a lot of opportunity for us to deploy robot, right? To free human being from working in such a production line, right? Then human being can focus on the design and the marketing and the sales, right? Okay, so good enough that you roughly have an idea. Then how to study this course? Recommendation is to put yourself into the mindset of a designer, right? Then ask this question of who are the user of a robot, what are the need of your user, right? Then what are the robot are you going to offer to the buyer or user, right? And then how to develop or design, implement your robot. Okay, so we want you to become a designer of a robot. Then what are you going to learn from this course? Okay, so this course will cover 3 modules among these 4, because we do not have time to cover advanced perception. Because we have another course, 4A29. 4A29 will cover the module about the advanced perception. Okay, and we also in parallel have a course of 4A32, which is a microcontroller or robot's brain. Okay, then you leverage on the content of 4A23, right, to complement your study. Then we just cover the module about the advanced body, advanced planning, advanced control. Advanced planning also help you to understand the scope of a study of AI, right, or 4A29, etc. Okay, so this will be the scope of study for this course. And this is a textbook, right? So you have a lecture slide, not textbook, help you to better understand the content. And for part 2, I guess we will ask you to do a small group project. You can use Robot Studio, implement something, and also robot construction set, right? You will have opportunity to do a little bit of practice, right, with the design of the robot. Okay, this is the learning objective. Okay, so the major objective is for you to become designer of the robot, and with the learned knowledge and skill, you also should be able to operate robot or to become a user of the robot. Okay, clear? And how to apply learned knowledge? Follow this blueprint, and this blueprint will guide you to design a complete robot system. Okay, from this blueprint, you will see inner loop, inner control loop, control of the motion, and the outer AI loop. You see outer loop, you have a robot intelligence, robot man, kinematic dynamics, etc. Right? Okay. So basically, to summarize this slide is you have an inner control loop, outer AI loop. Okay. You follow this blueprint, you should be able to come out the design of any advanced robot with intelligence inside. Okay. And we have this robot studio for you to use. Okay. Amma will be in charge of guide you or providing guidance to you for experiment, hand-on practice. Okay. And you may also heard of ROS. ROS is free. Okay. This slide gives you a little bit of guideline. ROS is a library function which help you easily to establish intermodule communication. And you must follow the terminology of a ROS, such as a package, not okay, application, right? Okay. Inside application, you have a lot of package. Inside a package, you have a lot of not. Okay. Then how to communicate amongst the node or module. So the ROS support two-way of eventually three-way. Okay. And you will just use two-way of communication. One is publisher subscriber model of communication. Another is a server client model of communication. Must think in that way. Okay, it provides you two model of communication. Okay, one model is publisher subscriber. Another model is server client. That's it. Okay. As a user, you choose any one that you want to use. So it's very, very easier to use ROS to build up a distributed system. You can treat robot as an IoT, mini version of IoT, Internet of Things, right? So you have a processor, you have an actuator. Think in that way. And the ROS, you can say ROS is a software platform for you to develop, implement IoT system. Think in that way, then you understand what is ROS. Otherwise, you get lost. Okay, IoT means the Internet of Things, a big system, right? That is the hardware, processor, sensor, actuator. That's it. Then what is the software support to IoT? Answer is what? ROS. Very simple. Okay, clear. So up to you to choose, because ROS is free. Then for those of you, if you want to choose to do certain project, my recommendation to you is to join the NTU Robotics team, right? This slide gives you a little bit of background knowledge about the autonomous surface vehicle and the Robotics competition, etc. Right? So there's a website there. You go to the website, then you will see updated information. Okay. But 2026 competition will take place in Singapore in November, right? So all of you are encouraged to join or to watch the RoboX Challenge 2026. Okay, clear. And for assessment, just I already mentioned, CA 60%, exam 40%. Okay, so that's about the quick introduction of this robotics course. Now let's move on to the study of module 1. Okay, module 1. Okay, module 1 is about the study of robots' advanced body. Okay, I can skip the slide at the beginning, so okay, because just now I already mentioned all these things, right? What is the current state of the art in humanoid robot? I just play a little bit this video, give you idea, right? So this is showing you the extreme motion performance, right? Okay, should be good enough. Okay, now we enter the study of module 1. So module 1 include a lot of topics. Okay, so in this week and next week, we just cover the hardware aspect of module 1. Then from week 7 all the way to week 13, Amma will teach you the theoretical aspect of module 1, which include robot static, robot dynamics, robot kinematics, right? Because this module is extremely important and heavy, right? Because you have a lot of hardware, a lot of theory, okay? So I just help you to understand the hardware aspect of module 1. Then theoretical aspect of module 1 will be taught by Amala, right? In the second part of this course. And today, we just quickly clear the study of lecture 1, lecture 2. Lecture 1 basically is a revision about the control theory because I guess all of you have done the study of a control theory, right? Lecture 1 is a quick review about what you have learned, right, from control theory. Then we apply what you have learned to lecture 2. That means consider mechanic system of a robot. Then what should be the key consideration for you to design mechanic system of a robot? Because mechanic system of a robot is the system under control. Remember, for control theory, there are 3 basic building block: system under control, feedback module, control module, right? Understand? System under control, feedback module, control module, right? So for robot, system under control of robot should be robot mechanic system. That's it, right? Okay. So let's start with a quick review about what you have learned from control theory. Because control theory basically is a theory about the control of a system. So you must know what do we mean by a system, right? System consists of a set of entities which interconnect together and act together for achieving common goal, right? For example, a robot has a lot of link, has a joint, right? Many other components. They interconnect together, then they can deliver motion, for example, right? Okay, so this is just a self-test for yourself, and put your mindset into this kinds of thinking, all right? And in future, when you see the whole world, and automatically pop up this keyword system, right? The whole universe is a system. The whole world is a system. NTU is also a system, right? And your home is a system, right? Okay. A robot is a system. A car is a system, all right? So there are plenty system in your real life, okay? Once you see the keyword system, automatically pop up 3 questions. What is input? What is output? What is the inner process which will produce output from input, right? Automatically ask yourself these 3 questions, okay? And in terms of the way to operate a system, so there are 2 ways to operate it. One is directly let the system to respond to the input. Okay, you must pay attention. This slide help you to understand a lot of research work under the title of reinforcement learning. Because this is a tricky terminology. What do we mean by reinforcement learning? Answer is what? They know nothing about the control. Then they try to find out what should be the input which will produce the desired output. Okay, if you know control theory, immediately you know this is a stupid way to find out the answer, right? Try all the possible input, then to see among all the possible input, what should be the subset of the input which will produce a desired output. Okay, for human being, okay, for certain application you can do so, like a demonstration, etc. But for majority of application, we never do that, right? So we use control theory. Okay, this help you to understand those speculation on reinforcement learning, right? That is open loop. But if you know control theory, this is the beauty for us to design the system which will be closer to the best system in the whole universe. Okay, you must keep this terminology in mind. Best system. Okay, our mission is to design dynamic system which will be closer to the best system. Okay, open loop, you can never achieve a best system, right? You just play the game, right? If you do the gaming, it's okay. Performance to play the Kung Fu, this is a performance, right? It's a dancer, right? Okay, that is not application. Okay, for gaming, it's okay. You can do all kinds of experiment, but for sophisticated application, must follow this. Okay, so design a system which responds to the error, right? This is the only way for us to make any dynamic system to be closer to the best system in the whole universe, right? I guess you know already what is control theory. Okay, so for any dynamic system, there are two types of response. Transient response is no good because it wastes our time, wastes our energy, right? So now you see why static systems are the best system in the whole universe, because static systems have no transient response. Okay, the purpose of designing a good dynamic system is to reduce transient response, right? Okay, clear. Then what do we mean by transient response? Okay, it's a transition from one steady state response to another steady state response, etc. Okay. If your dynamic system is not the static system, then you must care about the stability, response time, response accuracy, right? Okay. Now, based on these three criteria, immediately you understand how come a static system are the best system in the whole universe. Because a static system can achieve 100% stability, 0 response time, 100% accuracy, right? Okay. Very easier to understand, right? Okay. So then this is a revision of what do we mean by stable system, unstable system, rise time, peak time, settling time, all these, okay, are the component for us to judge response time. Okay, very, very simple. And accuracy, we define error band 1%, 2%, 3%, 5%, whatever, right? Okay. And today we are able to achieve a zero error, right? That means error band is 0%, right? No error at all is achievable. Okay, that is about the system. Then all the concept in the previous slide apply to robot. Robot is a special system, right? So robot has a lot of modules, right? They interconnect together, work together, right? Try to imitate human-like skill, human-like intelligence, right? Okay, then welding require a human being can do welding. Then we can have a robotic arm to imitate human-like welding behavior, and the human being also can do the loading, unloading of machine part into CNC machine. We can also use robot arm to do the similar activity. Human being can do the packaging, right? And we can use robot arm to do the packaging or whatever, right? And this is a spot welding, right? Human being can do spot welding. Then robotic arm can also do spot welding. Okay, so robot is a system which has an input, which has an output. But pay attention. Our expectation is to let robot to accept task description and the action description, motion description. Okay, but however, today's progress in AI have not yet reached this mature stage of making today's robot to achieve understanding of text. Okay, so pay attention to all this ChatGPT speculation. All right, the first step of a ChatGPT is to convert text into numeric number, and this step immediately destroy the meaning, okay, inside the text. Okay, so immediately you know it is useless, right? Because we should extract the meaning from the text, not destroy it. Okay, clear? So we need to do for simple case in industry, we should be able to make robot to understand a simple version of task description with the use of a human language or natural language. Okay, so later on we will, for the module about the motion planning, we will repeat a little bit this issue, right? How to achieve level 1 intelligence, level 2 intelligence, etc. Right? Okay, clear. So then the robot will have an output and also have an inner process. Okay, now we want to know, okay, inside the robot system, what are the sub-module which will enable a robot to produce output from the input. So actually, inside, they must be 5 subsystems inside, okay? Power system must be there, communication system must be there, okay? So just like I mentioned, a robot is a mini version of an IoT. IoT means what? It's a network of a processor, sensor, actuator. So communication system must be there, okay? Robot can output motion. Motion is a manifestation of a kinetic energy, right? So robot itself is an energy system. You must have a power, right? Okay. But most importantly, robot must have a mechanic system, control system, programming system. Okay. So these 3 are very, very important. Okay. On top of a power system, communication system. Okay. But for advanced robot, you must incorporate vision system, speech system, etc. Right? Clear? Then what do we mean by mechanic system of a robot? Okay, and how complicated it is? Actually, it's very simple, right? The mechanic system of a robot consists of a link and the joint, right? You have series of links, series of joint, right? They interconnect together. So this is a typical example of a robot with 1, 2, 3, 4 joint. You see the cylinder, the symbol of a cylinder that represent the joint, right? And then the line correspond to the link, right? You see link, join, then form a robotic arm, quite straightforward. Okay, this video summarizes the component inside an industrial robot or robotic arm. Okay, that gives you a big picture about the basic component inside robotic arm and also some terminology, right? So you see axis, right? So this is terminology in robotics. And then you have a more than one axis. Axis number 2, number 3. Number 4, right? So number 4, twisting. Number 5 is a pivot, right? Okay. Then number 6 also twisting. Number 6 is twisting, right? Then at the end of the arm, we can attach tool, right? The hand or tool. Okay, and for each axis, there's a motor, right? Actuation. We can inject energy. And then we have a handheld device to do the programming, right? And you see, we can write the small program, right? And which tell robot what to do, okay? So you need to study 4H32 in parallel microprocessor system, okay? Then you better understand the robotic brain or robotic mind, right? Okay. These are the tools for us to attach to the arm, right? Reaper. Right? Okay, this basically give you the overview about the basic component inside industrial robot. Then this slide summarizes what you have seen, right? Normally, a robotic arm has many axes. So we use a small cylinder to represent the axis, right? And also you see there's an axis layer pass through the cylinder. That is axis of a motion, right? So we may have a rotational motion, translational motion, okay, something like that. And how to represent a motion which rotate about the axis. Okay, there's a very interesting mathematical tool which is called as a quaternion, right? So this is a background knowledge for you to know, right? And interestingly, this is linked to what you have learned in control theory. In control theory, you have a Euler equation, right? And look at the Euler equation, you just consider J is any axis of rotation. Omega is any angle of rotation about the axis. Then you have a compact representation of a rotational motion. Then how to apply rotational motion to any vector in space. Then you see it just times them together, Q times V before rotation. Then you obtain V vector after rotation. Very, very simple, right? Okay. So this is a very, very efficient mathematical tool for you to describe rotational motion about any axis. Okay. And this tool actually is extension from Euler equation. And I guess all of you are familiar with the Euler equation, right? Because in control theory, I guess you have learned what is the Euler equation. Okay, this just for you to know. And then here is a example of a scalar robot, right? Then you see how many axes of rotation, 1, 2, 3, 4, right? Axis of rotation. And on top of a mechanic system, each axis must be powered by actuator. Okay, that means we must inject energy, right? And all the actuator must link together, must be put into the control of a microcontroller. Then this slide help you to understand this statement, right? Any robot is a mini version of IoT. Keep this in mind, then we will make your life easier. Okay, then you will pay attention to IoT, to ROS, okay? How to construct IoT, and also motivate you to study 4832 microprocessor system, right? Because without the knowing microcontroller, you do not know how to design IoT. And this will also motivate you to study ROS, how to program IoT. Okay, the most powerful tool is ROS. ROS is free. You see, then through the terminology IoT, you can link robotics to microprocessor system to ROS, right? Okay, so this slide is very, very interesting, right? Okay, and how about programming system? So this is also very important because the robot is for user to use. How to communicate with your robot. And in the introduction part, I mentioned human-robot interaction at the cognitive level. That means in future, we want robot to master human language, right? But today, we have not yet reached that level of intelligence for robot. And then at least we must have a programming tool, okay? Through the program language, we should be able to instruct robot what to do, okay? And this slide is important for you to know because objective of study of this course is for you to become a designer. Then as a designer, there's a requirement. You must make your robot to be programmable. Okay, that gives you motivation to pay attention to the study of a motion planning. The purpose of doing motion planning is to know the algorithm of doing motion planning and translate all these algorithm into library function, which will be offered to the buyer of your robot. Understand this requirement. As a designer of a robot, you must offer library function to the buyer of your robot. Understand? So this is why you need to study motion planning. And with algorithm of doing motion planning, then you are ready to translate all these algorithm into library function. Okay? Without the library function, you cannot sell your robot to the buyer. Clear? Okay? So it's just for you to know. And that's about the robot system. Okay, you see, basically there are 5 systems inside a robot, a basic version, right? If you have a basic version of robot, at least there must be 5 systems: power system, communication system, mechanic system, control system, programming system, right? These are the 5. But for advanced version, you can include a vision system, speech system. Okay, up to you. Okay, then how to judge performance of a robot? Criteria is similar like control system, stability, response time, response accuracy. I just play a little bit of this video, give you idea about the response time, response accuracy, stability. Right? This robot is stable, very fast, very accurate, right? Okay, so good enough. But for biped walking, there's an issue, right? For biped walking, how to make a robot achieve a stable walking is an issue. I play a little bit this video like you see today. Even for RoboCup, right? Their performance is quite poor, right? Even for this year, you can watch like the RoboCup video, right? So not much improvement, right? Okay. I just played it a bit. You see when the the robot fall, right? Okay.
Auch die Detektion des Handgriffes, das bringt ein paar Sekunden, in denen man reagieren kann oder frei agieren kann, sollte es das andere Team checken. Und das sieht gut aus. Beide Teams haben es erkannt. Zweikampf jetzt in der Mitte.
Okay, so you see, and I guess this is still a issue, right? Okay, just for you to know. And this is just a small example for you to understand stability of a biped walking. Very, very simple. Another example to understand stability with a wheeled vehicle. But for wheeled vehicle, this is not a big concern because the margin of stability is quite large. Okay, but at least you go through this example, you know, right? There's an issue of stability even faced by wheeled robot, etc. Okay. Response time, you see this demonstration now, right? Very, very fast, right? Okay. So we can shorten response time, but we cannot achieve a zero response time. Okay, this is just for you to know. Okay, we can make response time as small as possible, but not to make it to become zero. Not possible, right? In theory. And this is just a small example for you to go through. I guess solution is very easier, but this is just an example. Prepare you to study another module about the motion planning, right? It's just a warm up. I guess this is a year one physics, okay? So you have a starting point, you have an final position, then what is the shortest response, okay? And we give you maximum acceleration, deceleration, okay? The travel distance, right? You know, and we want to know what is the shortest response time. Then in this case, you as a designer, we design two motion. One is maximum acceleration, another motion is a maximum deceleration. Pay attention for this application. The slider initial position is 0. The final position must stop at the 20 cm. You cannot say I just pass through. It's not this scenario, understand? It just must stop there at the location 20 cm. Velocity must be 0. You cannot say I fly over. that is too simple, too easy. Okay, because a lot of application is I go from A to B, stop at the B, right? You cannot say I pass through B. That is too simple. Okay, clear? So this is why this is the profile of velocity, maximum acceleration, then maximum deceleration, then stop at the final position. Okay, so this is a planning already, right? If you choose this velocity profile, this will shorten the cycle time. Then the rest is very simple because this is the motion with a constant acceleration, constant deceleration. Then you know what is the travel distance for phase 1, travel distance for phase 2, for phase 1 travel distance and the velocity function, and for phase 2 what is the travel distance. Okay, then total travel distance is 20 cm. So you use this constraint, right, to find out what is the equation for you to compute t. T is a total travel time, right? Okay, then in this case we give you the detail of the solution now. Then response time is 4 seconds. Okay, you see, it's not the 0 second. Okay, clear. That is about the response time. How about response accuracy? You see this toy humanoid robot, right? The motion is very, very shaky. You can start asking yourself, how come the motion is a little bit shaky? Okay, then later on you will see, okay, I guess when we talk about the design of a mechanic system, we will use a speed reducer, right? when the speed reduction ratio is too small, then the output motion is shaky, right? You can reduce that error by increase speed reduction ratio. Okay, this example for you to understand, right? The relationship between error at the tooltip and the error at the joint. Okay, but this understanding will help you to study, better understand, pay attention to the actuator, to the sensor, right, which will measure the angular velocity of a joint. The measurement error will be transferred into the error at the tooltip. So this example is for you to notice. Okay, at the joint we have an error. This error may be the error of a sensor. Okay, then help you to know the error of the sensor will contribute to the error at the tooltip. That's it. Okay, so this is a very, very simple example, but the knowledge, the truth behind it is for you to know relationship between error at the joint and the error at the tooltips. Okay, so for this purpose. So then this is a scalar robot. We just look at the two link in the horizontal plane, like L1, L2. Very simple mathematics, right? So theta 1 drive L1, L2. Theta 2 drive L2. Okay, pay attention. Okay, theta 1 will drive the sub-assembly between L1, L2. Then theta 2 will drive L2 only, or eventually sub-assembly after L2, if there is, right? Interpret in this way, okay? So then what is the absolute orientation of L1? Then is the theta 1. Okay, pay attention, theta 2 is a relative angular position between L2, L1. Then what is the absolute orientation of L2? Answer is what? Theta 1 plus theta 2. Okay, theta 1 plus theta 2 is the absolute orientation of L2 with respect to the world coordinate system. And you will do the study of this in the second part of this course. Okay, Ahmad will teach, when he teach you robot static, robot kinematics, you will, okay, you will work out the more complicated example like this, right? More complicated example. This just help you to warm up or prepare you to study robot kinematics. Okay, just pay attention to absolute orientation of each link, right, in the world coordinate system. Okay, once you know orientation of each link, then you can determine, let's say, y coordinate of the tooltip. Okay, come from contribution by L1, L2. L1 will contribute to the displacement along the y-axis by L1 times cosine theta 1. Okay, L2 will also contribute to the displacement in y direction by L2 times cosine. You see, now is theta 1 plus theta 2. Okay, you compute first order derivatives. Okay, then you get the variation equation. Okay, very, very simple. You can easily, it's year one mathematics. Okay, then you consider worst case scenario. Worst case scenario is what? Sine equal to 1. Then theta 1 equal to the maximum error, right? Then you can evaluate the worst case scenario for error at the y4, right? Then you get the 0.0018 cm. Okay, so this help you to know, okay, the tooltip error come from contribution of error at the each joint inside robotic arm. Okay, clear? So this slide help you to, okay, link sensory error to the tool tips error. Okay, good enough already, right? The next question is how I'm going to design a robot mechanic system, control system, programming system. Okay, so and this is a guideline for you to follow. I guess this guideline is general, which is applicable to any product, any mechanic system. Okay, first question you must ask yourself, who are the user? Second question, what are the needs of the user? Third question will be, what is the product? What is the prototype that you are going to offer, which will meet the need of the user, right? Then next question will be, what are the functionality of your product, of your system? The next question will be, what are the solutions for you to achieve each functionality? Okay, so once you know the solution for each functionality, you can draw morphological chart. Then you can come out all the possible combination. That is conceptual design, right? Once you have a conceptual design, then you must have an evaluation criteria, right? In terms of a cost, appearance, reliability, etc. Okay, then you choose the best combination, right? Then once you have the best design solution, then you come out detailed design and the detailed part join, etc. Okay, so these are the procedure for you to follow. Okay, then on top of that, if let's say you want to design a mechanic system, what should be the key consideration? So you must pay attention to the design tasks, such as design of appearance, design of a mechanism, design of a structure. Okay, but for industrial robot, appearance is not important. But for service robot, appearance is very important. Okay, then what should be the key consideration for the design of a control system? Okay, so these are the 3 guidelines. Okay, you must consider, right? What are the input device? What are the output device? Okay, input device include sensor, all kinds of sensor. Let me input to control system, right? Sensor. Output device include actuator, right? You output energy, output motion, right? Then control device means a controller, right? So this is why you see 4832 is very, very important course for you to do the study in parallel, okay? Then for programming system, it's also very big topics, right? Because for this system, you must know the design of electronic brain and also AI. AI basically, okay, you must think in that way. AI is about the study of a design of a teachable mind. Okay, this is very, very important. If a mind is not teachable, how can we talk about the machine learning? Because a lot of work under the title of machine learning actually have nothing to do with machine learning. They are just doing data mining. Data mining have nothing to do with machine learning. You ask yourself, okay, because all of you are expert of learning, okay, so we know what is a human learning. So machine learning must be similar to human learning, right? All of you are expert of a learner. Then you ask yourself, okay, what is your way of doing learning? Okay, compare that with all those research activity about the data mining. Can we call data mining as a machine learning? Okay, the answer is no. Okay, clear. So this slide actually touch 2 important discipline. One is the design of an electronic brain, another is AI, right? Okay, so this is a very, very big topics, and we cannot afford okay, to spend too much time to talk about the design of programming system. Only focus for you to pay attention is to offer library function for the user to program your robot. That is a must, okay? Let's say you offer library function which can be called through the use of a Python, C, C++, C#, whatever, okay? This is a must for you to know, okay? Then how to design teachable mind, how to design programmable brain, that is not your concern. You should not worry. But this, you know, okay, the robotics is in connection with the electronic brain and the AI courses. Okay, good enough already. Okay, so that's about the lecture 1. Now we zooming into the specific guideline for the design of a mechanic system. Okay, what are the basic building block inside inside robot's mechanic system? The answer is a link and the joint. That's it. Very simple. Conceptually, very simple. You have a link, you have a joint. Then through the assembly of a link and joint, then you can come out the robot mechanism. Okay, and eventually, then you can put in the structure. Okay, then you come out the design solution for robots mechanic system. And the link just is a system, is a body in which is a rigid body in which you can house other electronic component like a sensor, electronic component, communication device, whatever. and eventually a cable, right? Whatever there. So it's a rich body. Inside you can house, okay, a lot of component inside, even computational unit, etc. So it's very simple, okay? And mathematically, you just pay attention to the two extremity of the link because we will attach coordinate system. Okay, there is a convention in robotics for any rigid body, we must assign coordinate system which will represent position orientation of this rigid body. So link is a rigid body. We must also assign a coordinate system. Later on, we will telling you the convention to follow for the assignment of a coordinate system. Okay. So then how to design a link? There's no specific guideline, or depends on your application or requirement. Okay. The link can be any kinds of a shape, up to you. Okay. No specific guideline. Okay. And here are some example of the link. Okay. And two adjacent link will connect by the joiner, right? So, and in that sense, we may have a terminology to name the link which is closer to the base link, right? Because for a series of a link, you always have a number one link, number one or number zero link as a base link, right? Number zero, number one, number two, etc. Okay. Then for the two adjacent one, the one closer to the base link is called as a supporter link, right? The one is far away from base link is called as a follower link, right? Okay, so in this way, you can name this is a supporter link, this is a follower link, right? And these two links share same join or interconnect by a join, okay, something like that. So this is another example, okay? A joint will constrain the motion. Okay, this is another convention in robotics. Each joint will only enable one degree of a motion. This 1 degree of motion could be rotary motion or translational motion. So this slide showing you translational motion. Okay, so you see the link can, in this case, only undergo translational motion. Okay, clear. And then what are the parameter of a link? Important parameter is the two extremity. So you have one closer to the base link, another one is far away from the base link, right? Closer to the base link, we call it as a proximal extremity. The other one is a distal extremity. Now you can ask yourself, where to attach coordinate system to a link, right? Is it proximal extremity or distal extremity? Okay, so you must follow convention that you cannot blindly assign, right? Okay, I guess convention in robotics is to assign it at the distal proximity. Okay, so the distal proximity, the coordinate system represent the position orientation of the link. Okay, this is a convention adopted in robotics you must follow. So on top of that, we can talk about the link length law. That is the distance between the two extremities, right? So the link length is not the actual length of the rigid body. Okay, pay attention, all right? So link length is the distance between the two axes pass through the extremity. You see the joint, right? Okay, it's that distance, it's not the actual, okay, the rigid body. Pay attention, okay? Otherwise, you get everything wrong, right? If you wrongly specify the link length, then all will go wrong. Okay, clear? So, and okay, and third convention is how to name label the motion axis. Convention in robotics is to name it as a z-axis. You cannot just name it as an x-axis or y-axis. Then you all get wrong, right? So it's a z-axis. Motion axis is a z-axis, okay? Then what we have is the x-axis and the y-axis. There's a convention for you to follow, then determine x-axis and y-axis, okay? You will come back again to this concept when you are going to study part 2 of this course, okay? Mark will tell you, we'll repeat all this concept. Today is just for you to warm up, okay? Know this convention of assignment of a coordinate system, and the naming of the coordinate system, okay, and the kinematic parameter of a link, all these things, metrics of a link, etc. Okay, So then this is an example, all right, motion axis, all right? You have a link 1, link 2, and the motion axis of link 1, link 2, okay? You spend time to visualize, right? And pay attention to this slide, okay? Then, okay, just like I mentioned, convention in robotics is to assign coordinate system at the distal extremity, not the proximal extremity, okay? This is convention in robotics, so you just follow, okay? Now you see for link 1, coordinate system, link 2, coordinate system, link 3, coordinate system. Pay attention. The location of a coordinate system of a link 1 is not at the joint 1. Now you see joint 1 is a distal, is a proximal extremity, right? Then coordinate system assigned to link 1 is at the distal proximity. All right, pay attention to this notation, all right? Try not to say, okay, the coordinate system assigned to link 1 is at the joint 1, then totally wrong. Okay, look at this slide, right? Coordinate system of a link 1 is not at the joint 1. Okay, remember this statement. Otherwise, you will make a mistake. Okay, clear? Then if you have an end joint, then you see all the end coordinate system. Pay attention. The Earth could be considered as a link 0. If your arm is on the table, then the body of the table is a link 0. If the arm is at the shoulder of a humanoid robot, then the shoulder of a humanoid robot, it will be considered as a link 0 or base link, right? Base link is link 0, okay? So now you see the coordinate system assigned to the base link, okay? It is at the proximal extremity of a link 1, okay? You follow this slide, you will know the relationship, okay? So it's quite simple, but quite important. Try not to confuse yourself, okay? Follow the convention, then you will not make a mistake, right? Okay. Then on top of assignment of a coordinate system and the kinematic parameter of a link length, what are the other parameters? Actually, in total, there are 4 kinematic parameters, okay? Not just one, the link length, right? So this table helps you to know these 4. We put together, we call them as a DH parameter. Okay, in the second part of the study, you will learn more about it. Here, I just give you the summary, okay? So you just look at the motion sequence, which will bring one coordinate system to superimpose another coordinate system, right? Sequence of a motion make 2 adjacent coordinate system to superimpose together, right? First one is to rotate about the z-axis. Then there is one kinematic parameter, which is a theta I, right? After that, you translate along the z-axis, right? That is a kinematic parameter of a di, okay? You see the di. Then we rotate about the x-axis. Then the angle is alpha I. Then translate along the x-axis. That is a displacement of ai. So through this use of these 4 kinematic parameter, you will be able to transform one coordinate to be superimposed with another coordinate system, all right? So this fully describes the relationship between 2 coordinate systems, okay? So this is the DH parameter. So then if you apply these 4 parameter, you see rotation first, rotate, okay, about the I-1 axis. So you have a coordinate system assigned to link I, coordinate system assigned to link I-1, okay? So look at the notation, rotate about the z-axis of a coordinate system I-1 with this theta I angle, followed by translation along the z-axis of a coordinate system assigned to I-1 link, right? Then followed by rotation about the x-axis, okay, of the coordinate system assigned to link I-1. Then lastly is a translation along x-axis of the coordinate system assigned to link I minus 1 times together, you will get a 4x4 matrix. That matrix represents position orientation of link I with respect to link I minus 1. Okay, that means we always talk about where is the coordinate system assigned to link I with respect to the coordinate system assigned to link I minus 1. Okay, try to be used to this description. So in part 2 of this course, you will spend more time to be familiar with this description. Okay, and if you are not familiar with this, then you spend a little time to digest this slide. Okay, clear? So that's about the link. Okay, once you know link, then next is how to join two adjacent links together, right? So you have a supported link and the following link. Okay, so in the textbook, the description is very simple. It's just a robotic drawing done already. But this may not help you to understand control. Okay, so here I split robotic joint into 3 types. We have a link joint, we have a torque joint, we have a power joint. Okay, this will help you to better understand the control system of a robot. Otherwise, you will see the discrepancy with the description about the design of a robot mechanic system with the design of a robot control system. Then terminology will fight among themselves. Okay, so it's better to talk about the link joint, torque joint, and the power joint. Torque joint basically is a speed reducer, right? And the power joint basically means actuator. Okay, when we describe in this way, immediately you understand design of a mechanic system of a robot strongly depends on the design of actuator, design of speed reducer, all right? And they're strongly related to the design of a control system. Because when we design control system, basically we talk about the design of a control of a power joint. Understand? When we talk about the robot control, basically we talk about the control of a power joint. Through the control of a power joint, we achieve the control of a link joint. So it's better to do this decomposition. Otherwise, when you do the study of a robot control, you may get lost already. Okay, by splitting or decompose a robotic joint into these 3 types, then you can easily link this module with the module about the robot control. Okay, clear? So this is our approach, all right, to teach you the joint. Okay, it's not just a robot joint. Actually, inside you have a link joint, torque joint, power joint. Okay, clear? And in terms of a type of a motion, we have 2 types of motion, all right? Just now I mentioned that joint is a device which enable 1 degree of freedom. And this degree of freedom could be translational motion or rotational motion. If the joint enable translational motion, then we name it as a prismatic joint. And this type, you must associate it to the link joint. Link joint or, okay, so or eventually torque joint, right? Because we can always do the conversion between rotary motion to linear motion, okay? But this type of, classification, not much meaningful in terms of motion control, okay? But it's useful for you to do the motion planning or to do the kinematic study, okay? So then you need to know the type of a motion, okay? Whether it's a prismatic motion or revolution motion, etc. Okay, so then what is a joint? Joint in general is a device which take input mechanic energy, okay, then output mechanic energy. And in theory, we assume there's no loss of energy, right? Okay, so then the total energy output from a joint is equal for the linear motion is a force times velocity. for rotary motion is a torque times angular velocity. Consider joint as a power supply, right? Because the output from joint is mechanical energy, right? You can treat it as a power supply. Okay, this is conceptually for you to know, right? Joint is a device which output energy. Joint is also a device which output motion. Okay, you can output linear motion or rotary motion. And from mechanical point of view, a joint include link joint, torque joint, and the power joint. Okay, so these are the concepts which are related to the joint. Okay, in terms of energy output, in terms of motion, type of motion, linear, angular, and in terms of the device, physical device, okay, which allow us to implement the joint. So then we have a link joint, torque joint, and the power joint. Okay, so this cover the full understanding about the joint. Okay, clear. So this is a classification adopted by us. Okay, so it's better. Okay, to in terms of the hardware device, split into three types: link joint, torque joint, and the power joint. Power joint is actuator. Torque joint basically is a speed reducer. Then link joint is just a two link connect by the pin, right? The bearing, etc. Right? Okay. So okay. So how to design link joint? These are the solution, right? Okay. So I guess all of you know this, right? And one more example. And this also a solution for you to implement link joint, right? And due to time constraint, I'm not going to play this video. You can find from the YouTube how to design a slider, right? You can find plenty of such video. Okay, I just skip. Okay, these are different type of speed reducer. Okay, you can find easily from the YouTube. Okay, so to save time, I'm not going to repeat all this. Okay, one particular torque joint is this harmonic drive, because this device is very, very popular in the design of robot. Reason is because this device is very light. It can achieve a very high speed reduction ratio, okay, and very small. It's a lightweight, small in size, and high in reduction ratio. This is why it's very, very popular. And its working principle is very simple, okay? So harmonic drive has a three body. So you just pay attention to the rigid body 1 and the rigid body 2. In between, you treat as a rigid body 1 prime. So basically, there are three rigid body, and the 1, 2, and the in between. Okay, so speed reducer means what? Body 1 can be input motion. Body 2 then is output motion. Or body 2 is input motion. Then body 1 is output motion. Okay. Then between both motion of a body 1, motion of body 2, then there's a motion difference. Then what is the ratio? The ratio is speed reduction ratio. Okay. And the body 1 prime is we call it a flexible spline. And from this illustration, you will see body 2 has an inner. It's like a gear with the teeth, right? Then body 1 prime also has a gear. Only difference is the number of a gear in the rigid body 2 and the number of a gear inside the rigid body 1 prime. The difference is 2. Difference is 2. If the difference is 0, for example, the number of teeth for rigid body 1 prime is exactly equal to the number of teeth for rigid body 2. Consequence is what? When it rotates, there's no relative motion between rigid body 1 prime and the rigid body 2. Yes or no? Relative motion is 0. All right. So then in this case, when you rotate rigid body 1, then rigid body 2 will not rotate at all, because it will not produce a relative motion now, right? But when the difference between the number of teeth is 2, it means what? when the rigid body one undergo one full rotation, then rigid body two will undergo relative motion of 2 t's. Yes or no? If the difference is 0, then 0 motion. If difference is 2 t's, then the motion, relative motion is 2 t's, right? One full rotation move 2 t's. Based on this knowledge, you should be able to compute or design the harmonic drive with any desired speed reduction ratio. Okay, so this just for you to know. And the speed reduction ratio in theory will not dissipate energy in theory. Okay, it just redistribute the energy and the motion. So you look at this equation, right? You amplify the output torque, then you reduce input velocity. So you see the equality, right? Okay, so this is just for you to know. And then for the design of the power joint, basically it is motor. Motor, okay, have a two rigid body which could undergo relative motion, right? So the rotating one, we call it rotor. The stationary one, we call it stator, right? So they can undergo relative motion, okay? So we call this as a power joint. So for each joint, you always remember, there must be two rigid body one, rigid body two, all right? For link joint, it's the same law. You have a supporter link, follower link, that means rigid body one, rigid body two. For torque joint, same law, rigid body one, rigid body two. In between, you have a rigid body one prime, right? Same. Then for power joint, same. You have a rigid body one, rigid body two, right? Stator, rotor, then can undergo relative motion. And the power joint is a device which output mechanical energy, right? Quite straightforward, okay? Now, next question is we have a strip of a joint. Then how to combine them together? So these are the design option for you to choose. Okay, it's up to you based on your application. Option one, power joint plus link joint. We call it as a direct drive. This is another name, right? In research community, direct drive. That is a design scheme number one. Design scheme number two is popular. Design scheme number three also popular, right? Design scheme number two means what? Power joint, torque joint, link joint. Okay, so this will give you very, very compact design solution. And in case if you have more space for your robot body, normally people will follow design scheme 3 because design option 3 give you advantage of relocate power joint towards the base link. Because when the arm move and normally power joint is heavy and you will waste a lot of energy. If you put the power joint inside the body of the arm, you waste a lot of energy. So it's better relocate it at the base link. You save energy. Understand? So that is a design scheme 3. Okay. So which one to choose up to you, right? And this is an example. Okay. You see, this is one example done by us. You see our humanoid robot, full size. The leg basically follow the design scheme number 3. Okay. And the motor is slightly relocated, okay, outside the link joint, okay, slightly relocated, right? Then you have a torque joint, power joint, and link joint all together, okay? So this is an example. And in YouTube, you can find the plenty example, right? You see the animation, second animation is a digit humanoid robot, digit, right? And you see its motor, I guess, is inside the body, right? So its leg is very thin, right? It's like a chicken, right? Okay. So the leg is lightweight, right? Okay. This just for you to know, okay? And this animation help you to see how to do the coupling of a robotic joint, okay, which include power joint, torque joint, and the link joint. You see the motor, you see motor, you see harmonic drive, this is torque joint, right? And the link joint, right? So this is an explosion diagram. Then you disassembly, then you assembly all this together, right? Okay. Okay, this just give you an idea. So actual design of a robotic joint is an arm, okay? It's an arm, artistic work, right? You need a lot of creativity, a lot of physical work, right? It's not just like you key in the equation done already, okay? Maybe with the help of AI, right? In future, computer-aided design, then move on to computer design. Then you just tell, I want to have this type of design scheme, then it come out a solution for you, right? Okay. For those of you, if you want to do research in AI, this could be an area of topics for you to venture into. Okay. This is another example. I'm not going to play similar like a previous one. Okay. And okay, this example is to warm up you about the study of robot dynamics. Because when you design the power joint, there's one requirement called as a motor sizing. Okay, what is the power motor for you to choose? Okay, so this is a simple example for you to know how to choose the motor. This depends on the maximum payload and the maximum velocity. Okay, based on maximum payload, maximum velocity, you know the maximum power. Once you know maximum power, then you can choose the power of the motor. Because to choose a motor, one important parameter is output power, mechanical power. Okay, how to determine mechanical power? You can determine it based on the maximum payload, maximum velocity. Okay, so this is a simple example, right, for you to follow, and the solution is given to you. Then you can, okay, you can choose a motor with the desired output power. Okay, clear, right? Okay, now you know link, you know join. Okay, then you are ready to put them together. Then you form a robotic arm or body, whatever, a finger, hand, whatever. Okay, so a mechanism basically is a assembly of a joint and the link in series. Okay, eventually it could be in parallel or sequential, single series or multiple series which are in parallel. Okay, it depends on your creativity. I just play a little bit this video, give you a full picture about the whole cycle for you to design a robotic system, vision system, assembly, testing. Okay, you follow this video, actually you are able to implement a robotic project from scratch. Okay. So conceptual design, right? So this conceptual design, then you choose the actual one, then you come out the embodiment design, then part join. You see this is embodiment design, 3D view, then part join. Then you once you have a part join, you trigger assembly, fabrication, guided by your part join, right? Okay. But this is a compressed video, just highlight to you the key step. Then you do machining, right? And all the necessary part. After that, you do assembly, right? Okay, still this is a machining, right? Produce individual part. Okay, now you do assembly, right? Put, okay, related part together, then form sub-assembly, then put the sub-assembly together, then you have a robotic arm. And during the assembly, you also attach actuator. You see, just now you see the assembly of the joint, okay? Motor is a power joint, right? Eventually, there's a speed reducer, then you assembly a robotic joint, okay? And during the assembly, if you miss out some component, then you repeat, right? Design, then get the join, then you do the machining, then you continue your assembly, right? Okay. This is the assembly, right? You still need to miss out the component, right? Then you do the fabrication, right? Then you do assembly, right? Okay. And then you see then you do a little bit of manual testing, right? And okay, this is the design of a control system, right? Implement control system, you have a controller, sensor, monitor the signal. Once done, then you integrate a control system with the mechanic system, right? Now, I guess programming, again, is a design, right? You miss out some part, right? Then you design again, right? And print it out. I guess is to design the fixture for sensor, right? Fixture for sensor, limit sensor, right? For the motion limit, okay? Okay, after control system, now is programming system. Either you write the library function or use existing library function. If this is your robotic arm as a product, you must write your library function. And you see, this also include a simulation tool, right? Okay. You must develop a library function. And this is a controller. You see, robotic brain, camera is a vision. And actually, this is an advanced robot system. Okay. Also, it's very, very simple. Then it's calibration of a vision system, right? It's already an advanced robot project. Okay. And programming system, you do the testing, image acquisition, image processing. Okay, then is a demonstration of do the pick and place, right? Guided by vision. And then you will see this is a demonstration of a control motion loop and the AI loop planning and the perception planning. This is the AI loop. That means this demonstration include control loop and the AI loop, right? Okay. And a pick and put on top of another one, right? Or place somewhere and then pick the rest and stack them together, right? Then pick another one. You see, all guided by vision, right? Then place on top of another one. Okay, you see. And then there's also a virtual environment. You see the screen, right? So actually, this is a very, very advanced robot project, right? Done by a single student. You see, a single student. From conceptual design to the part drawing, to machining, to assembly, to programming, to testing, to demonstration, right? Done by a single student. Okay, try to demonstrate your capability, right? Similar like this student, all right? Okay, so then the remaining part just for you to know, okay, continuing study for theory. In the previous slide, basically we show you the hardware part of a robot body. Then how's about the equation of kinematics, equation of dynamics, okay? The theoretic study about the robot body. Then you will do it after 6 weeks. So Amma will continue the study with you, okay? Then pay attention to the input motion to robot mechanism, output motion from robot mechanism, relationship between input motion, output motion. What do we mean by robot kinematics? Okay, kinematic, we have a forward kinematics, inverse kinematics, and we also have a forward dynamics, inverse dynamics, etc. Okay, so then this is just a simple example of forward kinematics. If I know input motion, how to determine output motion? Very, very simple example. I guess you can easily work out just to warm up for you to be familiar with this concept of kinematics, etc. Right? Okay. And inverse kinematics is to determine the joint angle if I give you desired output motion, okay, etc. Something like that. Then for dynamics, basically it's a relationship between motion and energy, force and torque. Okay, so you will do the detailed study of kinematics dynamics in the second part of this course. Okay, then again, this is an example for you to know how to do the motor sizing, right? Based on the desired maximum output torque, what kinds of motor to choose. Okay, so you go through this very, very simple example, then at least help you to understand the issue of doing motor sizing, choose motor with the right output power. Okay, clear? Okay, so let's talk about the study of the second lecture. So we just end today's online lecture. Then subsequently, we make the lecture about the controller because controller will be covered by 4A32. I guess many of you already have experience with microcontroller. Then no point to repeat. The next lecture we just cover the study about the actuator, sensor, and a little bit the programming system because I guess your weakness more is more in programming system, right? Certain philosophy, certain guideline, right? Okay, so let's talk about today's online study. We still have maybe 5 minutes. It's already time already. Maybe a few minutes. If any one of you would like to ask question, you turn on your microphone if you have a question, all right? Or you can ask question during the physical lecture, right? Or unless if you have a urgent question to ask. Any question? If not, then we end today's online lecture. Then see you in the next lecture, physical lecture in the classroom, right? Okay.